Consider a 9-lead Y-configured motor necessitating a low-voltage configuration. In a low-voltage configuration, we need to create a parallel configuration. In this case, terminals 4, 5, and 6 are tied together to form the central junction of another Y. Then terminals 1 and 7, 2 and 8, and 3 are 9 tied together. Phase voltages L1, L2, and L3 would be applied to terminals 1, 7, 2, 8, and 3, 9. The motor connection diagram might illustrate a 9-lead low-voltage configured Y motor using a diagram similar to this. This low-voltage parallel configuration is almost like two Y configurations overlaid on top of each other. For this reason, low-voltage parallel Y configurations are sometimes referred to as YY configurations. Note, for a truly balanced three-phase AC load like a motor, you wouldn't ordinarily need to connect the two central junctions. Consider a 9-lead delta configured motor. In this case, the pre-wired windings only partially complete delta configurations. These partial deltas can be placed in series for a high voltage configuration or placed in parallel with one another for a low voltage configuration. Winding A1 has terminals 1 and 4. Windings A2 has terminals 7 and 2. Windings B1 has terminals 2 and 5. Winding B2 has terminals 8 and 3. Winding C1 has terminals 3 and 6. Winding C2 has terminals 9 and 1. Note terminals 1, 2, and 3. A 9-lead delta connected motor does allow access to both ends of an individual winding. However, note that at each corner, the manufacturer has already tied two windings together. Consider a 9-lead Y-configured motor necessitating a high voltage configuration. When you wire these windings in series or a high voltage configuration, 4 is connected to 7, 5 is connected to 8, and 6 is connected to 9. In this case, it creates a really large delta with each corner to corner from 1 to 2, 2 to 3, and 3 to 1 consisting of two windings in series. This series high voltage configuration is sometimes known as a big delta. Phase voltages L1, L2, and L3 would be applied to terminals 1, 2, and 3, pending desired direction of rotation. The motor connection diagram for a 9-lead high voltage configured delta motor might illustrate this configuration using a diagram similar to this. Consider a 9-lead delta configured motor necessitating a low voltage configuration. The parallel low voltage configuration takes some visualization skills since it's a little busy. In this case, terminals 1, 6, and 7 are connected together, forming the top corner of the parallel delta. Terminals 2, 8, and 4 form the right corner of the delta, and terminals 9, 3, and 5 form the left corner of the delta. When you squeeze the three partial deltas together, winding A1 is placed in parallel to A2, B1 is placed in parallel to B2, and C1 is placed in parallel to C2. You might want to pause the lecture and look at this one. First time someone showed me this, I stared at it for 20 minutes without blinking before I saw what they were talking about. The parallel low voltage configuration is sometimes called a delta-delta connection. Phase voltages L1, L2, and L3 would be applied to terminals 167, 284, and 395. The motor connection diagram illustrating a 9-lead low voltage delta might illustrate this configuration using a diagram similar to this. Moving on, consider a 12-lead three-phase AC motor. This motor is the most flexible in that it allows a technician to configure it for use with high or low voltage in either Y or delta configuration. In this case, both terminals of 2 windings per phase are accessible for a total of 12 accessible terminations. Winding A1 has terminals 1, 4. Winding A2 has terminals 7, 10. Winding B1 has terminals 2, 5. Winding B2 has terminals 8, 11. Winding C1 has terminals 3, 6. And winding C2 has terminals 9, 12. Consider a 12-lead motor necessitating a high voltage Y configuration. Terminals 10, 11, and 12 are tied together, forming the central node of the Y. Terminals 4 and 7 are tied together, placing winding A1 and A2 in series with one another. Terminals 5 and 8 are tied together, placing windings B1 and B2 in series with one another. Finally, terminals 6 and 9 are tied together, placing windings C1 and C2 in series with one another. Phase voltages L1, L2, and L3 would be applied to terminals 1, 2, and 3, where phase sequence determine direction of rotation. The motor connection diagram, illustrating a 12-lead high-voltage Y-configured motor, might illustrate this configuration using a diagram similar to this. Consider a 12-lead motor necessitating a low-voltage Y configuration. The parallel low-voltage configuration forms one Y by tying together terminals 4, 5, and 6. Then another Y is formed by tying together terminals 10, 11, and 12. The two Ys are placed in parallel by tying together terminals 1 and 7, 2 and 8, and 3 and 9. Phase voltages L1, L2, and L3 would be applied to terminals 1, 7, 2, 8, and 3, 9, where phase sequence determine direction of rotation. The motor connection diagram, illustrating a 12-lead low-voltage Y configuration, might use a diagram similar to this. Consider a 12-lead motor necessitating a high-voltage delta configuration. The series high-voltage configuration ties together terminals 4 and 7, placing windings A1 and A2 in series. Terminals 5 and 8 are tied together, placing windings B1 and B2 in series. Then terminals 6 and 9 are tied together, placing windings C1 and C2 in series. Then 1 is joined with 12, forming the top corner of the series delta. 2 is joined with 10, forming the right corner of the series delta. Finally, 3 is joined with 11, forming the left corner of the series delta. Phase voltages L1, L2, and L3 would be applied to terminals 112, 210, and 311, where phase sequence determine direction of rotation. The motor connection diagram, illustrating a 12-lead high-voltage delta configuration, might look something like this. Consider a 12-lead motor necessitating a low-voltage delta configuration. The parallel low-voltage configuration ties together terminals 1 and 7 and 4 and 10, placing windings A1 and A2 in parallel with each other. Then terminals 2 and 8 and 5 and 11 are tied together, placing windings B1 and B2 in parallel with each other. Then terminals 3 and 9 and 6 and 12 are tied together, placing windings C1 and C2 in parallel with each other. Then the 1-7 group is joined with the 6-12 group, forming the top corner of the parallel delta. Then the 2-8 group is joined with the 4-10 group, forming the right corner of the parallel delta. Finally, the 3-9 group is joined with the 5-11 group, forming the left corner of the parallel delta. Phase voltages L1, L2, and L3 will be applied to group 1-7-6-12, 2-8-4-10, and 3-9-5-11, where phase sequence determines direction of rotation. A motor connection diagram illustrating a 12-lead low-voltage delta configuration might look something like this. Let's see if we can put what we just learned to good use. Here's an example of a 6-lead motor. When we open the connection box, a handy cheat sheet pops out written in a number of languages. Even if you don't speak any of these languages, diagrams accompany it. As great as this cheat sheet is, expect it to be lost soon after the motor is installed. That's why motor connection diagrams are ordinarily scribed on the metal motor nameplate affixed to the motor. In this case, the motor has 3 coils, U, V, and W, and each coil has 2 ends, U1 and U2, V1 and V2, and W1 and W2. The terminal block is arranged quite cunningly in that a set of 2 jumpers can be used to connect the motor in either a Y or delta configuration. The 1 and 2 terminals for individual coils are not directly across from each other on the terminal block, but rather diagonally offset from each other. The purpose behind this diagonal offset becomes readily apparent when the jumpers are used to configure this motor in a Y or delta configuration. Note when we compare this cheat sheet to the initial state of the motor, we can see that this motor came shipped in a delta configuration. U2 is connected to V1, V2 is connected to W1, and W2 is connected to U1, forming a triangular delta configuration. The corners U1, W2, V1, U2, and W1, V2 form the connection points to the three-phase AC source, where direction of rotation is determined by the phase sequence. When we remove all the jumpers and check the resistance of all three coils, the ohm meter says that they're all around 42-ish ohms. When we reinstall the jumpers in a delta configuration, note that an ohm meter used to check resistance from either corner sees around 28-ish ohms, which is the series combination of two windings of the opposite corner taken in parallel with the corners being inspected. This is a great sanity check. 42 plus 42 is 84. 84 in parallel with 42 is 28. Because this is a balanced three-phase AC load, 2-point resistance measurements at all three combinations would yield the same value. We can rest assured that this motor is properly wired in a delta configuration. Using the cheat sheet, we can now remove the jumpers and reinstall them as recommended to produce a Y configuration. Using the angularly offset terminals, two jumpers connect the three terminals U2, V2, and W2, forming the central junction of the Y. Terminals U1, V1, and W1 would be used for connection to the three-phase AC source, where phase sequence determine direction of rotation. Note that an ohm meter used to check resistance from either corner of the Y sees around 84 ohms, which is a series combination of any two windings. This is a great sanity check. 42 plus 42 is 84. Because this is a balanced three-phase AC load, 2-point resistance measurements at all three corners would yield the same result. We can rest assured this motor is wired in a Y configuration. That's about it for dual voltage motor connection diagrams. Before we close up shop, however, I'd like to briefly touch upon dual speed motors. As discussed in the rotating magnetic field lecture, changing the number of active pole pairs in the stator changes the rotational speed of the rotating magnetic field, something called synchronous speed. The different configurations used for dual speed motors in effect change the number of pole pairs in the stator via one of two methods: consequent pole, meaning you get rid of some pole pairs by sending current in the opposite direction, or separate winding, meaning there really are different windings that you can connect or disconnect to change the number of pole pairs per phase. These configurations change resultant speed only and are not related to high or low voltage operation. The reason I'm not spending a lot of time on dual speed motors is because you're most likely not going to run across them unless you're working on really old equipment. Dual speed motors display a marked difference between high and low speed settings and have largely been replaced by a power electronics device known as a motor drive that varies excitation frequency, thereby directly influencing rotational speed. Varying excitation frequency rather than pole pairs per phase allows for finer tuning of rotational speed and necessitates no physical modification to a motor. In conclusion, this lecture discussed motor connection diagrams. We examined generic 3, 6, 9, and 12 lead motor connection diagrams and discussed dual voltage motors, Y and delta configurations, and briefly discussed multi-speed motors using consequent pole and separate winding methods. Additionally, we put our knowledge to practice and examined a motor and its associated motor connection diagram and used an ohm meter to confirm electrical configurations based upon the motor connection diagram. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource and be sure to check out the Big Bad Tech channel for additional resources and updates.